Here's some alternate paths for finding curvature. Theorem 12.8, if C is a smooth curve given by a vector valued function r of t, then the curvature kappa of C at t is also given by kappa equals the length of t prime of t, that's the derivative of the unit tangent vector, divided by the length of r prime of t, divided by the tangent vector. And kappa could also be the length of r prime of t crossed with r double prime of t, that would be sort of like the velocity crossed with the acceleration, divided by the cube of the length of the velocity vector, or r prime of t. So let's say without proof, I will just say that that's alternate paths. I could probably take some time and talk my way through that, but let's not and say we did. So the question is now, do we have a function? Remember these things, this is a length, so that is a function, this is a function, we can divide, this is a function, this is a function, we can divide. So here's what we want to do. We want to find the curvature of this space curve, ti plus 3t squared j plus t squared over 2k. And so the first thing to do is find r prime of t. That's I, derivative of this is 1 times I, the derivative of this would be 6tj, the derivative of this would be tk. So we've got r prime. So if we wanted the length of r prime, we have to find the length of this vector, which is the square root of 1 squared plus 6t squared plus t squared. Right there it is. So our unit tangent vector is, technically it's 1 divided by this plus 6t divided by this plus t divided by this, right? Actually 1 divided by this times I plus 6t divided by this times j plus t divided by this times k. But you know, before I go too far into this, you know, I'll need the length of r prime of t, which I think I already did that, because that's what this is right here. So I have that, but what I don't have is the length of t prime of t, and before I find the length of it, I need to find what t prime is. So t prime of t would be the derivative of this vector valued function. And believe it or not, I can use the good old quotient rule on this. So it would be down, d up, well, what's the derivative of this? 0i plus 6j plus k. So there's that part. Minus up, which is this vector. D down, well, the derivative of 1 plus, or the square root of 1 plus 37t squared to the 1/2, multiply by the 1/2, and then subtract a half as an exponent, and then multiply that by the derivative of the inside function. So we got a half times this to the negative a half, that's 1 over the square root of that, times the inside function, and right there it is, and all that over the denominator squared, right? Because it's low d high over, or minus high d low over the square of what's below. Want me to say that again? Low d high minus high d low over the square of what's below. Okay, and that is our derivative. That's the derivative of the unit tangent vector. And let's see if there's some way we can simplify it. Certainly we can take out that 0 and just make it 6j plus k. And this, the 74.5 cancel, giving us 37 times the r prime vector itself. And so now we get this mess as t prime of t, and so wanting to simplify that mess, what could I do? I could multiply out this entire numerator and collect up the like terms, so we'd have negative 37 ti. There's no I in this part, so, and then I'd have plus 6j and then plus 37t squared j, but look over here, I got minus 37, oh, it's 37 times 6. Oh no, it's 37, positive 37 times 6 t squared j. Here we got negative 37 times 6 t squared j, so that cancels out happily. So how do I wind up with this 6j? Don't forget this times 6j, so we got 6j, and then we have 1 times k, and then we have 36t squared times k, and then here we have, 37 t squared times k, and here we have negative 37 times t squared k, so they cancel out, but we still have this 1k. How about that? So that would be correct. That is a simplified version of t prime of t. And so now we need the length of that, which is the length of this vector. I got the length of r, that's here, right? That's the length of the vector r prime, I should say. So that's in the denominator. Now we need the length of this vector, which is, if you think about it, it's the square root of this squared divided by this squared when you find the length, right? And then this squared divided by this squared, and then this squared, which is 1, divided by this squared when you find the length. So I hope you see all that, but you know, I'd say divided by this squared and I didn't square it. So I'm thinking, instead of saying this to the 3/2, this constant that I would factor out would be just cubed. Didn't mean to undo that. Come on, give me a better undo than that. Give me a better undo than that. There we go. What I want to do is not divide that by 2. Right, there it is. And so I got a little mistake. I'll have to fix that as I move through this thing. And oh golly, what a mess now we got. So if I divide by this, square root of 1 plus 37 t squared, oh, I gotta get rid of this one here too. I guess what I'm doing is making this to the 7/2, right? When I divide by an extra one of these, this thing divided by that would put an extra, actually I could just even cut that and put it, no, oh, this could get worse. So how far back can I undo? I can't undo anymore. I goofed. So I got this, and I want to say times this. So now I think I'm cooking with gas. So let me see what else I need to fix up. This is wrong now. So if I simplify this, that would be, this denominator is 1 plus 37t squared to the 7/2. And so if I copy this, paste it in here. Well, actually, why don't I just say this? This square root of 37t squared plus 1, this 1 square root of 1 plus 37t squared cancels out. And if I can get rid of this 2 here, that's it. This is our curvature function. Wowie. That was a bit on the ugly side, but there it is.